we could get those lights any brighter, huh? Let's give people one more minute. I see people coming in. Is the lighting adjustable back here? Because it's really almost problematic for the speakers. Maybe you have already thought about that. Yeah, we're really flooded up here. Okay, we're going to give people about 30 more seconds. Okay, good morning, everyone. Hi. Yeah, that's better. We have seating for 1,500, so, make yourselves comfortable. My name's Jim Slata. I'm from the University of Toronto, and it is a great pleasure to be here today to chair the Rumelhart Symposium, the award given to Professor Mickey Chi, who was my doctoral advisor, and a session in her honor that was composed and put together by her. I'm going to say a few words about that to welcome us to our session. I hope you're enjoying this wonderful city, Montreal. It's a great place for a conference. Wonderful accommodations here at the Convention Center. And as a researcher at a Canadian institution, University of Toronto, I'm welcoming you as well to our wonderful nation. So for those of you who don't know Mickey, and I'm guessing that would be not many in this room, she has been a leader in the field of cognitive psychology. I don't want to say how many years, but I know there were publications in the late 70s, and it was her original work in misconceptions of physics that drew me to work with her, and her great reputation and respect in the domain of expertise. That was kind of one of her original areas, followed by, you see here, a set of topics that aren't even exclusive in conceptual change, misconceptions, self-explanation, tutoring, and then more recently, the ICAP framework that has drawn a lot of recent attention by educators. In fact, she has so many awards. I've listed a few of them here that it's, this one I'm sure takes the cake, but over here. I didn't list it at the bottom, but we should list the Rumelhart Award below the Thorndike. And I think it would be nice of us to ask Mickey to stand up and just give her a well-deserved round of applause for an incredible career. And a very, very well-deserved award. And I know that you'll learn more about her work as you move forward. I should say that she's incredibly well cited. I just put this here for humor. For those of you who are worried about such things as citation indices, I think she gets more in a single year than most of us are going to get in our careers. It's over 50,000. Okay, Mickey doesn't worry about citations, but that's wrong. I drew that off of Arizona State University website. So, and I'm sure that this ICAP framework is going to get some more massive citations. So the theme that Mickey chose for her session, and this is indeed one of her curation, and you can imagine that in other cases people would put this together with their students or with senior researchers to sort of situate their work in the field. And Mickey's take on it was to focus on the notion of translational research in STEM learning, and that is an area where she has made a huge impact. In fact, cognitive science and cognitive psychology in general are the kind of fields, I can speak with my own experience, that are well suited to that kind of translation. But this is work where we take it from the lab, we take it from the theory, and we situate it in the rich complexity of practice and of real-world context, in particular in this session, teaching and learning in K-12 STEM. So I thought that my own experience was, as chair of this session, I kind of reflect that spirit, because I was Mickey's student in the early 90s, 91 to 96 at LRDC, University of Pittsburgh. How many here have some connection to LRDC, University of Pittsburgh? I have found that any crowd, and especially in the cognitive science or psychology, there's an incredible percentage of us that trace some connection back to that incredible place that Mickey was instrumental in putting together with Bob Glazer, Lauren Resnick, and a whole bunch of others, that I was really honored to be part of that as a student. But my own background coming in was in physics, artificial intelligence, and robotics, and I was drawn to thinking about how people learn physics, and that's what brought me into Mickey's research group. I was her first ever graduated PhD student, so that's something they can never take away from me. But on graduation, I did feel like the stuff that I had been working on, which was related to misconceptions and conceptual change and robust misconceptions, was really applicable to the world of K-12. And I found a postdoc out at UC Berkeley that was just starting a project on integrating the web into K-12 science. And so I jumped at that, and that sort of made the difference for me, and I went on to a long career in the educational field, working in K-12, and my current work at University of Toronto is to run a lab of my own that involves research practice partnerships, co-design with teachers, working very situated projects, learning across contexts, informal and formal. So it's very exemplary of the kind of translational work that Mickey sought to represent in today's session. So here's what we're looking at down here in the front row. Today's session is titled Translational Research in STEM Learning, and I want to say hello to anyone on the webcast as well. We have 4 speakers who represent and were selected for their interdisciplinary, multidisciplinary, transdisciplinary work. And I've had a wonderful chance to meet them over lunch yesterday and get to know them a little bit better via email. So they are Christy Boyer from the University of Florida, Kristen Butcher from the University of Utah, Percival Matthews from Wisconsin-Madison, and Jody Davenport from WestEd. So we're going to go in that order, give the speakers about 20 minutes each to present, and I've been asked if we can hold our question and answers till the end. This is for the purpose of the webcast. So while they're transitioning from one speaker to the next, we can have a couple of clarification questions that I will happy to help field, and then at the end we'll bring all 4 of them up on the stage to do the Q&A. Okay, so on that, let's welcome Christy Boyer, an associate professor in computer information science and engineering from the University of Florida, and her presentation will be collaborative dialogue and tutoring to support computer science learning. Welcome.
Thanks, Jim. All right. I don't think I'll be very successful at standing right here, so gentlemen in the back, may I use this handheld microphone? Is that okay? I'm taking silence as yes. All right. Okay, so I'm really excited to get the chance to share with you about how Mickey's work has influenced my line of research. So unlike many of the other people you'll hear from, I didn't have any direct, close mentoring relationship with Mickey. Her influence on my professional career has been through her scholarly publications and the times that she has shared her wisdom and insight with me at conferences. So I decided to tell this as a story and share with you the 2 pivotal moments where her work was especially influential, but these are just a subset of the number of times that I have built on her work and been influenced and inspired by it in my own research. So this is my research lab. We are in a department of computer science within a college of engineering, and we do interdisciplinary work collaborating with a lot of educational psychologists and learning scientists and disciplinary education researchers. I identify as a computer scientist, and my work focuses on how people use natural language dialogue for teaching and learning. And the majority of the context that I study is computer science teaching and learning. So that's what this talk will focus about. It'll all be in that context. So I started out my career looking at undergraduate computer science education. I was really interested in how people are learning computer science in those early courses that are so important for STEM undergraduates. So here's an example from one of my early projects called Java Tutor, where two students are working together at a computer. We call it pair programming in this setup, and they're debugging some kind of code, and they're relating the things that they're doing to the things that they've recently learned in class. And I study the dialogue that these students exchange, as well as their emotional expression through their facial expressions, posture, and many other multimodal sources of input. And over the years, I became interested, and I'm going to tell you the story of how this happened, in studying younger and younger learners and how they learn computer science. And so some of my most recent work is focused at the elementary school level. This is an example of one of our kids' programs where they decided to make a princess go pet a horse, and they told this story through their code, and then running the code caused the program to display the story. So these are two very different kinds of writing computer code. One of them is very textual, and you can see there are semicolons and curly braces. They're sort of the quintessential stuff of jokes when it comes to learning computer science. But we know that block-based programming, which is what is shown in this slide, is really helpful for younger learners. So that's what we use with younger students. There's a lot of things in common about the dialogue that these learners exchange, whether they're doing textual or block-based programming, and I'm especially interested in the ways that they're coming to make sense of the concepts that are common across those two contexts, as well as how they're doing the pragmatics of dialogue. How are these kids asking questions, giving each other feedback, sort of managing their discourse at that pragmatic level? So you'll see what I mean by that in just a minute. I thought I would give you a bit of a timeline of my life. I'm going to do it in like 2 minutes, I think. And then you'll see why I'm doing that, I hope. So I'm not going to put a year of my birth because Mickey was asked to choose younger researchers to give these talks, and I'll just let you imagine that I'm quite young. So I was born in Georgia in the United States on a dairy farm and was raised there in a rural area. I did my bachelor's degree in math and computer science. I was the first person in my family to go to college. And then I did my master's degree in statistics. I really had fallen in love with both computer science and math, and I thought, what could I study that would let me bring those two things together? So I studied stats within a department of industrial engineering. Then I spent a little bit of time being a software developer at Delta in an operations research department. I wrote code that helped the baggage drivers to drive your bags to the plane on time. That was very exciting. And then, after I did that, I became a lecturer at the university where I had done my undergraduate degree. So I taught 4 or 5 classes every semester, which was really fast-paced, both math and computer science classes. And it was at this moment in my timeline that I became really interested, for the first time, in how people are teaching computer science, partly because I reflected on how very poorly I had done it in my first few times. So I was interested in doing research in how people teach computer science, and that's what led me to the PhD program in computer science at North Carolina State University. And now I am a flip-flop wearing professor at the University of Florida in computer science. So it was at this moment, now I'm going to put a year, I'll quantify this now, back in 2006, when I was a new graduate student, and I was just shaping the direction of my dissertation. Now, I had come to graduate school very sure that I had done a poor job as a lecturer of computer science and math, and that there was a lot of pedagogy that could be done so much better across our institutions of higher education, and I knew how to do it. I mean, I was really sure that all I needed to do was build some kind of an AI, that would tutor students on how to do programming, and that would be this huge revolutionary difference. So that was my brilliant idea, and I mean, it's a good idea, but I didn't know how to go about it. And as I started contemplating how could I do a good job of building an AI that would tutor programming, I read Mickey's first paper for me, which was her journal article, Learning from Human Tutoring, from the Cognitive Science Journal. And this paper completely shifted my perspective on what I wanted to do as a graduate student, because it hadn't dawned on me that I should study what humans do. It dawned on me to be critical of my own approach and try to do better, but it didn't dawn on me to observe the richness of human dialogue and learn from that. And Mickey's paper examined hypotheses about, is it really the contributions of the tutor that make tutoring so effective? Because one-on-one tutoring is super effective. Is it what the students do? Is it in the interaction between them? Is it something else? And this way of asking the question made me aware of how much we don't know about how people use this interaction to support a really high level of learning. So it kind of shifted the entire course that I think I would have taken, along with, of course, lots of other influential literature. And then my first paper ended up being titled The Influence of Learner Characteristics on Task-Oriented Tutorial Dialogue. It was actually 2007. There's a typo on my number there. And this paper examined what are the ways in which students with different backgrounds, maybe different levels of self-efficacy. At the time, I also examined different gender, different levels of incoming knowledge. How does that influence the way that these students interact with a human tutor? And I found some significant differences based on those characteristics, not only for the types of things that the students would say, but also the types of things that the tutors would say, even when the tutors didn't know ahead of time these students' characteristics. So the study that I used to examine this question was actually a computer-mediated remote tutoring study where the two participants, the tutor and the student, were located in different rooms, and they were collaborating through a synchronized integrated development environment with their Java code, and they never even saw each other. In most cases, they actually didn't even necessarily introduce themselves by name. They just sort of jumped right into the task. So I was really interested in how that rich interaction brought these big differences based on who the student was, even when I didn't tell the tutor who the student was. So I knew I was really intrigued by this and wanted to go deeper. And I decided that what I wanted to do was take an approach. So this is kind of a framework approach to the research that I've done since then, and even continuing in large part to now. And that is that I start often with observational studies of humans. In this case, it says a tutoring study, but I actually have transitioned now and do primarily collaborative dialogue between two peers or near peers, not so much a tutor context right now. And then I move into the annotation phase, which is where, of course, I take that corpus that I collected of human interaction and mark it up in some meaningful ways that make it easier then to apply machine learning approaches and learn models of the data. And then I model the data and use it in some way within an implemented system. So many of my systems have been dialogue systems, but there is some variation, as you'll see, in the sorts of things that we've built using this overarching framework. So one of my first projects was the Java Tutor project, and it was this computer-mediated tutoring that I mentioned to you before. It was a web-based integrated development environment that supported remote collaboration. And just here's a quick example of the kinds of dialogue that we see in an interface like that. The student says, so do I have to manipulate the array this time? And the tutor says, this time we need to do two things. First, we need to create a new array to hold the changed values. Now, I didn't instruct my tutors what approach to take, and this particular tutor, I remember who he was because he ate more of my sandwiches than the other tutors. That's how I paid them, was in sandwiches. I was a grad student. So the tutor took a fairly instructive approach, just sort of giving step by step to the students, especially early on. So this was the first time, as far as this tutor knew, that the student had ever created an array to hold values. So the student started typing int, it's going down there, and then realized, oh wait, I don't want an int, so they delete, 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 and then they realized they wanted it to be a double, so that's DOU. They're starting to type double, which is a kind of floating point value in Java. So that you can see, as we examine this kind of corpus, the evidence of both what the student is doing, as well as how that is interleaved with what the tutor is saying, as well as what the students are saying. Interestingly, it looks like I don't have any student utterances in these examples. Our logs also show us when students get things like runtime exceptions, which is what this is. All right, so once we have these corpora collected, this text, we move on to that annotation phase. And one example of the ways in which we annotate our data are through dialogue acts. So there's a really rich sociolinguistic theory of dialogue acts. I omitted every single literature citation-heavy slide from this talk for the interest of time and to make it more like a story. So I'm happy to give lots of citations after if you have any questions. But here's an example. So we tagged when tutors would do things like give a hint versus a directive. So a directive is do this, and a hint is more indirect and lets the student, or hopefully lets the student infer what action should actually be taken based on that hint. Acknowledgements are really important. Those are one of those things, interestingly, that differ significantly by the learner characteristics, both for tutors and for students. They can request feedback. They can give positive, lukewarm, and negative feedback, ask questions, give answers. And this is one scheme, but we often go into much more detail. So we have an entire taxonomy of questions, for example, that we sometimes go tag those and then build separate models sort of in a hierarchical way. Once we have our corpus tagged, one of the things that I did early in my work was to build hidden Markov models of the dialogue that the students and tutors would exchange. So instead of the entire textual utterance, we would build models of the sequences of dialogue act tags. So for example, you've got a dialogue act from a tutor, a student, you've got a task action like those deletions or insertions of code. And for every single student and tutor session, we would have this sequence of observations that we had collected and annotated. And then the idea of hidden Markov models is that it sort of probabilistically extracts a higher level latent structure that's on top of those observations that we collected and labeled. So the nature of that latent structure is left to our interpretation. And in my early work, I called these strategies. I called those boxes that are around the sets of observations strategies. I wouldn't call them that now because I think that they are more clusters of different types of acts, but back then I called them strategies. And then that allows us to build models of the ways in which people progress through the strategies or clusters or modes. We've sort of tried to work out the vocabulary of them over the years. And then we can not only build models of the sequences of observations, but also models of the sequences of strategies. And as a grad student, I was really interested in whether the strategies, these latent structures that nobody could directly observe and which I couldn't with any confidence defend what they represented, but I was really wondering, are they correlated with the things that we really care about? And it turns out that they are, at least in some cases. So when we discover those tutorial dialogue strategies with HMMs, we can then characterize the effectiveness of the tutorial dialogue with these, and it's just correlational, so we can't make any causal conclusions about what it is exactly that, that was contributing in these studies that I did early on. But the idea is that the more that certain ones of these clusters or latent structures would appear, the more effective we saw the tutoring in terms of learning gain. We also looked at gain for self-efficacy and found some interesting differences there. I was excited to tell you about some of them, but I decided to move on quickly. All right, so that's a few things that I worked on during my graduate student years, and I'm going to skip a bunch of time. Here in the 2006 era, reading Mickey's paper was such this transformational thing, and there were two other events over some years that were, similar magnitude. Having my children. So reading Mickey's journal article and having a baby. Thank you for laughing. Oh my gosh, I was really nervous that you weren't going to laugh. Okay, so there's my first kid, born my second year of my PhD studies. And then my second kid was born my first semester as an assistant professor. So I just picked like the easiest time ever to have kids and wouldn't change it for anything. All right, so now the interesting thing is that these were really influential in my professional career because there was this moment where I sent that first kid off to kindergarten. Now, I hadn't even thought about how little kids experience classrooms in schools. Had not thought about it, wasn't even interested in thinking about it. Thank you. But when my kid went to a classroom, I had all kinds of scholarly interest that got piqued, right? So I guess maybe that may have happened to some of you. So put together, these really ignited for me an interest in studying collaborative dialogue in elementary school. So now you might notice that many years had gone by between the work I just highlighted to you and what I'm about to talk about now. And in that time, I had established a funded research program that examined not only undergraduate computer science learning, but also middle school computer science learning and game-based learning. So this was kind of a natural step to me to look at younger kids, and I noticed some things when I would visit classrooms. So I noticed that sometimes when kids in an elementary school classroom, I visited 4th and 5th grade, collaborate, sometimes it goes really well. Sometimes one kid will say, well, I think, and then the other kid will say, oh, let's try that. And now this kind of gives away the fact that I'm pretty much always looking at task-oriented dialogue. Let's try that. So these kids are really not discussing concepts. They're not engaged in sort of argumentation. They're trying to do something. In my case, they're trying to write some kind of code. They're trying to make the puppy run in circles or the princess pet the horse or whatever it is that their goal is. And so they contribute their ideas into this shared task workspace. All right, so that can go well. Somebody can give an idea. The other one can uptake that idea, and then they do it. Sometimes it goes okay. In fact, this is actually really great. I would take this any day. One kid says, I think, and the other one says, maybe, say more. That's awesome. Love that. Other times, often, it goes like this. One kid says, I think, and the other one says, that's dumb. And then the observation that I made was then oftentimes one of these kids would come away feeling that they're bad at this, and the other kid would come away thinking, I'm really better off doing this alone. And as I observed this phenomenon in classrooms where it was really blatant, these kids, they don't filter what they're saying. They'll just say that's dumb out loud. I realized this was also happening with my undergraduate students when they were in pairs. I realized that compared to 4th and 5th graders, my 19 and 20-year-olds were really not any better. And so I had to do something about this, and I decided that had to mean writing a proposal to NSF and getting funding to study this phenomenon. So I started writing the proposal and submitted it when my kid was in 1st grade, and then I resubmitted it, and then it got funded when he was in 5th grade. So it was one of the harder sells that I've ever had to a review panel, was that kids can and should engage in collaborative dialogue, and in my case, I really cared that it be about how to develop a sense of computational thinking and learn about computing. So as I was writing the proposal, I had this really brilliant idea, and that was the kids are together. Those orange figures are the 2 human kids, and they're talking, and they've got to be instrumented somehow, so they're going to wear a headset, and then there's going to be this virtual agent, that's the burgundy red-colored character on your right, and it's going to be talking to the kids because it will hear what they're saying through the thing, and then they're going to be coding. It's going to be great. And then, as I'm writing, I realize this is just going to be awful because there's going to be all these interpretation errors, because even the best attempts at doing automatic speech recognition for kids are very errorful. So I was kind of stuck. Then I remembered something. I remembered standing outside of Mickey Chi's talk when she came to visit Duke University years before this proposal was being written. And we were standing there in the foyer, and she was telling me about this study she had done of having kids watch other kids get tutored in physics, and how this vicarious learning was so exciting. And I immediately went and looked for the paper, and I thought, okay, I have an idea now. My idea is, let me use the lessons that Mickey found, and it opened more questions, of course, than it gave answers, but that's what good papers do, on observing tutorial dialogues collaboratively. Let me use that as a powerful potential ground for creating this technology that I want to create. So the idea went from, what if there was just this one virtual agent? What if there were 2? What if they had dialogue and the kids collaboratively, vicariously watched this dialogue? Could that be a way to help these kids learn to have dialogue well and learn about computing? And that's what we are in year 2 of 4 of investigating. So once I made that realization, we got the project funded. And now we are in the middle of doing it. So we do participatory design. We went through an entire year-long process to get kids from sketching what good collaboration looks like all the way down to the final design of our virtual characters. This is work that was done in collaboration with Eric Wiebe and Colin Lynch from North Carolina State University. And then we also have made some findings about For little kids, maybe the logistical setup that they need could be different from what undergrads need. Maybe the two kids sitting together at the same computer isn't always the best solution. Kids don't have the same regulation abilities for sharing. So I'm really excited, this is my last slide, about what the future holds about moving forward in this project that is the result of one of these turning points inspired by Mickey's work. So we are in the middle of classroom deployments. This work is being translated into classrooms even as we speak, and hopefully will benefit thousands of kids once the system is done. It's in 4th and 5th grade, and we integrate it not only into technology electives in elementary school, but also into science classrooms. So we build coding-based exercises where kids practice science concepts through computing. All right, so I'll wrap up. I want to acknowledge all the colleagues I've had over the years, my lab, my faculty, co-PIs, James, Brad, Eric, and Colin, and then the Intel and Media Group at NCSU who've been collaborators over the years. And then we'll wait and have questions at the end, I think, of all the speakers. So I'll turn it over to our next speaker. Thank you.
We can take that.
Jim says if you have any quick clarification questions.
Your mic's dead already.
Just kidding.
Yes?
The hit markup modeling work that you did earlier, did you wind up applying that to collaboration as well?
The question is, can you guys turn this on? The question was, had we applied the HMM, the hidden Markov modeling framework, to collaboration? Yes, I have a PhD student, Fernando Rodriguez, who has recently been applying the HMM framework to collaborative dialogues, not just tutoring dialogues. Yep. All right, thank you.
Wow.
Nice. Okay, the next presenter is Kristen Butcher. She's an associate professor from the Department of Educational Psych at University of Utah, and her talk will be Designing Learning Environments for Effective Cognitive Engagement.
Thank you very much. Good morning and welcome. It's an absolute pleasure to be here as part of the symposium honoring Dr. Mickey Chi, who has had tremendous professional influence on my work, is a wonderful mentor and also a friend. I was Mickey's postdoc in Pittsburgh at the LRDC as part of the Pittsburgh Science of Learning Lab. I searched in vain for an old lab picture of all of us, but apparently 2007 was a simpler time when we didn't document every aspect of our lives. This was as close as I could come. But Mickey's influence on my work started before I was her postdoc. Like the other speakers in the symposium, even though my current work is really about learning practices and education, and it takes place largely in classrooms, I was not trained in education. My background is as a cognitive psychologist. I did my graduate work at the University of Colorado at Boulder, working with my advisor, Dr. Walter Kinch, and I studied text comprehension and comprehension processes, typically in a lab, often using indirect tasks like inference verification. Towards the end of my graduate career, I became really interested in understanding how visual representations change the learning process. We knew that visuals changed learning, in fact, improved learning. We used to strip them out of any learning materials that we'd bring into the lab to study text processes with. And I really wanted to understand in real time what was changing about learners' comprehension processes such that it created these improvements. I needed a way to study this, and I turned to Mickey's work on self-explanation to really try and capture students' learning processes in real time as they were engaging in a task. And I studied learning with different materials, so either text alone or text with a variety of different visuals, finding that learners' more shallow processing, such as these paraphrases that you see, it's a little hard to see the pointer, didn't really change very much, but their deeper processing, these inferential processes, changed significantly when visuals were added to a text. So that gave me an understanding of what is the process rationale for these outcomes. I was heavily influenced as well by Mickey's work on quantifying qualitative data, not only in looking at those utterances that students were producing as they were learning, but really trying to understand the mental models that students were taking into a learning task. And I think it's really indicative of the depth of Mickey's thinking to know that she had published these potential prior mental models that were extracted from localized utterances across the learning episode that students had made, and they are eerily similar to the actual visual representations that students drew in my study when I asked them to draw and explain their mental model at the start of study. So it really shows how she can really use those processes and quantify and understand what students know going into the task. More recently, I've been influenced by the ICAP framework, which I understand Mickey will talk about later today. Don't miss that talk, where we can think about the depth of different kinds of activities that take place in classrooms. And certainly we see this in our studies. We see this full range. So students who are, in terms of their overt behaviors or products, not really doing much, maybe doing something active but not producing new content, to producing new content in the form of written products, maybe physical products, or utterances where they're talking and developing new content. Those conversations that students are having can reach into that interactive space where students are co-constructing, they're building on each other's statements to develop new content. But we're really focusing and thinking about this constructive area. We want to focus students in on this constructive set of processes and activities. And I think the ICAP framework has been really helpful in both communicating to others kind of where we're operating, but also helping us think about situating where we are in terms of developing activities and environments and thinking about what kinds of things we ought to be supporting and why we think that they are really helping students learn in deep ways. I should mention that the ICAP framework is a theory that applies across classroom activities and education, so it purposely doesn't make a distinction among the depth of activities that can occur at the constructive level. If you're going to apply a framework across a large variety of domains and tasks, you wouldn't do that. But for domain-specific activities, specific concepts, or specific instructional components, I think it's useful, and I'm going to try and show you how we've tried to develop a framework for the depth of constructive activities in a specific area, and hoping to convince you that we've been able to see some progress in defining depth according to a theory-based framework, reliably measuring that via student utterances, designing and evaluating learning environments based on that, and seeing alignment to unique student outcomes. So we're building upon that ICAP framework for a specific area. The work I'm going to talk about today is part of an interdisciplinary team, and I think the translational research that we all are doing often is very interdisciplinary. So I work with the Natural History Museum of Utah, and this team includes domain scientists from the museum studying new areas of science, museum educators, curriculum developers, us learning researchers, and graduate students from a variety of areas. The specific work that I'm talking about today was funded research where we were tasked with trying to figure out how to support critical thinking in science investigations. And I think this is a nice example of translational research because it's very applied, it's very educational, but the problem with trying to support critical thinking is that it's often very broadly defined and not consistently in the research literature. So you have everything from this just purposeful judgments to reflective and reasonable thinking. They're all accurate to some degree, but they're very general and so not that helpful in actually constructing learning environments or specific activities. And I have to say some people take a more dispositional approach to critical thinking, but we find it helpful to be trying to think about the actual cognitive processes involved in critical thinking. And you can mine the research literature for a range of these cognitive processes that have been studied in the context of critical thinking. And you you can align them then to a progression of science investigations. And so this first column really concerns the production of ideas. The second column is really looking at building evidence through a variety of constructive processes. And the last is really looking at how students are strategically analyzing. If you think of these processes in the ICAP framework, they're all constructive processes, but maybe they're not all created equal for this specific activity and domain. So this is where my background as a comprehension researcher comes to bear, which is I think of comprehension, or these constructive processes, also in the framework of levels of comprehension, particularly from the construction integration model proposed by Kinch. And so we're going to ignore that passive category for a second and talk about the levels of comprehension and how they might map onto ICAP. There's a surface level, which is really this exact representation of materials, probably really just at the active level. Text space in comprehension is not often thought of as a very deep process. It typically involves manipulating the materials that you're given, but I think there's this gray area where you are constructing things, but simply from the materials that have been provided. The situation model is used to refer to the level of understanding that is developed when incoming information is integrated with prior knowledge. The representation is flexible and allows transfer and application, and it really allows you then to construct these deeper forms of content. So if we think of the level of depth that's required from the ICAP framework, within the ICAP framework, you're in construction, and then if we add comprehension onto this, we can think of 3 different levels, which is when you're generating from materials, when you're integrating those materials or constructing with prior knowledge, or a level where it really requires both the integration of the incoming information, the prior knowledge, and some level of inferential processing. So with increasing depth as we go up this scale. This means we can organize these processes into really a framework of depth and critical thinking. So we've organized the constructive processes into this framework, reflecting the progression of a scientific investigation and the processes at different levels of constructive depth. We've looked at this in a series of classroom studies that were initially performed in 6th grade classes. And we're using authentic materials from the museum in digitized form. So we did laser scans of fossils from the museum that were both 3D printed and produced as virtual models for the students. You can't see it in this photo, but there are camcorders that are recording how students are interacting with the materials and each other, as well as voice recorders that provided us with the transcripts of other student utterances for us to analyze. You might not be able to read this from the back, I don't know. It's not important to read the exact words. It's just showing how we created a coding rubric for the utterances from the framework of constructive processes at different depths. We then coded students' conversations as they worked on these tasks. And I should say that we worked with the paleontologists from the museum to create an authentic question that students were using those materials to answer, and they were tasked with developing an evidence-based argument to answer the question. We did verbal coding on students' conversations. This research is not for the faint of heart. We coded about 10,000 utterances per study. We got excellent inter-rater agreement, so it does show that we can reliably apply these codes to students' conversations. And about 44% of what students are talking about as they're having these conversations falls into those critical thinking codes in that framework. The other things that they're doing, some off-task talk, talking with a teacher, and then a category here, activation, where they're really just kind of rereading materials or restating what they're given, and so not constructing something new. If we look at just the pilot alone, so this was the very first implementation to see how did the task work and does our framework apply reliably to the students' conversation, We saw that in these first two categories, as the investigation was progressing, students were heavily kind of concentrated in these lower levels of depth, and probably because they were tasked with creating evidence-based arguments, they had more sort of balance or movement into sort of those medium levels of depth in that last category. However, if you looked at students' work products, they were entirely disappointing about the kinds of evidence they were using and how they were using evidence, probably not unlikely due to the fact that they were staying in these very low levels of depth during that evidence building stage. And so we use this to decide where do we target our revisions in this learning activity? How do we create revisions that should support students' processing and increase depth, particularly in that stage? I don't have time enough to go into all the detailed revisions, but just at a general level, we increased the number of reference materials, the additional models of fossils that were available to them, provided space to document comparisons, and kind of restructure their work products to help them focus on evidence gathering and evidence-based thinking throughout the task. If we look at, now this has changed so that this is only the evidence building stage across the 3 studies, we see that from the pilot, this top row here, where students were very heavily concentrated on those lower level depth of processing, we were able to increase the medium and higher levels of processing in the next 2 studies. These both use the same design, and so we do see consistency across these next 2 implementations. We use the lessons from these studies and this implementation to then design a digital learning environment that would then scale much more broadly to classrooms. You can see the dinosaur investigations online, and we have a new set of investigations also using digitized resources for authentic investigations that we are developing at this time. These investigations use these digitized models of the authentic museum objects, the libraries of existing museum comparison objects as well. And also we've digitized other paleontology resources that paleontologists use to analyze what's happened at a dig site and to make inferences about the patterns of what they're seeing. 5 minutes, oh, okay. We also digitized the scaffolding that's included in the investigations. So we've included the paleontologist from the museum modeling how she makes inferences based on observations, how she uses patterns of evidence to make judgments and look at reasons. We also structured the work product to try and capture the collaborative construction that was happening as students talked. One of the things we noticed is that students often weren't engaged in effective processing. That kind of got lost to the ether. They didn't keep those constructed pieces of knowledge available long enough to really reflect on them. So we used that to structure the work product. We looked at this again in 6th grade classrooms, the digital model. We are recording the screen and students wear lapel mics so that we can capture their conversation as they're working in an environment. And I think I'll have just enough time to play this video, which kind of shows you how students are talking and working with the system, as well as some of the potential pitfalls and fun of classroom investigations. Can we hear? Oh, wait. Oh, I did plug in the thing.
Shut up. I'm gonna slap you. I don't like this. Neither do I.
It is. Can I start it?
Oh, yes, we love this. We love this. Yes, we do. I was saying I don't like this because of my partner.
How do we do the extra?
I am apologizing. Your website is a great piece of modern technology with 3D models of real dinosaurs that you have loaded into the database from your workplace, and you have created this in such a particular way that it will be the pinnacle of learning.
Okay, anyways. How did we go to the X-ray thing again? I kind of forgot.
The box.
This?
Yeah, that box. And then the invisible one. Yeah, that one.
Yeah, boy. No, I want this one. No. That one. Okay, so it does kind of look like it. Not necessarily. Well, actually, it doesn't. Because this one has more sharp teeth. And this one, well, maybe the sides broke off, but
So you hear at first what's happening, and you missed the very first part. They kind of fight over the resource a little bit. Who's messing it up? I get a brown-nosing soliloquy for a little bit, but then they get down to business, and we actually see this a lot, where they're engaged with the task and the tools, so then they start producing some talk. They start changing their mind. They're like, it looks like it, well, not necessarily. Wait, actually, it doesn't. And then they start to try and infer or create an argument about why they may look different and whether, in fact, they actually are different or not. So you sort through, when you go from the lab to the classroom, you sort through a lot of talk. But I do think that what we get is this real time of how do these investigations play out and what's happening in the classroom. If we look at the actual kind of depth of processing, this is across the different stages of the investigation in these digital studies. And we like to see that we are getting increasing depth as we proceed through the investigation. And we also want to know how does that translate into outcomes. So one of the things we look at is this sort of like does this generalize to critical thinking strategies? So they're not specifically taught critical thinking strategies. We hope that they're developing an understanding through these authentic investigations. So we include items that are testing things like that are not critical thinking, but include vocabulary and terminology that they may associate with science and that are addressed in their classrooms, like looking for a piece of evidence to kind of prove your ideas right, or trying to find evidence that would prove your ideas wrong, which is indicative of critical thinking, but not really that appealing to them until after they've engaged in a full investigation. We see, compared to matched control classrooms, that students who engage in those actual, in the learning environment and doing the authentic research do much better at recognizing and agreeing with true critical thinking strategies following instruction, and that their performance on that deeper measure, that more generalized measure, compared to a skill-based measure of observation, the depth of process doesn't predict performance on that more skill-based measure, but it does on the generalized measure. We've also did a study looking at whether this environment supports teachers. So we looked at whether or not teachers who implemented by themselves actually were able to achieve the same results as researcher-based implementation, and we found no difference in researcher implementation and teacher implementation, but improvement compared to control classrooms for both. So I think the ICAP framework has been super helpful for me in thinking about where am I operating to make sure that we're operating in the correct space and to think about how we can build on that for specific tasks in specific areas. And so finding ways to theoretically define what we're doing, to align it to learning outcomes, and to really think about how the depth of processing is translating into student outcomes that are deep and meaningful. Thank you.
We've been asked to hold all questions, indeed, to the end. So we will try to get the new presenter set up in a hurry. This is Percival Matthews. He's an associate professor, Department of Educational Psychology at the University of Wisconsin-Madison. And he is going to present a talk for us called So What's the Big Idea? The Importance of Knowledge Structures for Promoting School Learning. That.
Hey. All right, thank you. So it's great to be here. And how my thought was deeply affected by Mickey started with my second stint in grad school. So once upon a time in grad school, I was a political theory student looking at things like Kantian morality. which was fun and all, but a lot of political theory talked about what people did, but they weren't particularly interested in testing what people did. So it was time for me to leave. But while I was there, part of how I paid the bills the first time was working for a small educational consulting company. And when I was working in 2001, there's this No Child Left Behind thing, and the government says that we need to use research-based instruction. And when I started to try to look for that, a lot of what I found was sort of like what I saw in political theory. There were lots of ideas in education research, not the psychology side, but on the education side, that were often enough good ideas, but they weren't things that people were testing. Again, it was like doing physics without the friction. Your spaceship blows up. So I wanted to know, what would research-based instruction look like? How could I go about this? And just as a neophyte going in, I thought, well, psychology sounds pretty good. You know, we could start with some basic science of cognition. We could distill some design principles and maybe package it for teachers, but I don't know how to do this. How do I do this? So I started with this lady and reading her one of her papers by accident on self-explanations. It took me to Bethany Riddle Johnson, much respect, to Mickey Shi. And so with Mickey, from the beginning, there was this sort of abiding appeal that she had. You know, whether we were talking about chess experts or physics understanding or this double loop model for understanding a circulatory system, it was deeply about how knowledge structures could go a long way. And it was this big idea can go a long way by the time you got to this circulatory system. So she also was operationalizing engagement as a way to build and organize these knowledge structures with self-explanation as a practical route. So from the way that I was coming into education, something about these top-down processes with engagement was really appealing. Now, I'm not a CogSci heretic, right? I believe in statistical learning. I like that I learned how to walk. Like, these sorts of things aren't how we're going to learn how to walk. You know, language, don't leave home without it. But when it comes to some of these higher order things that we learn in schools, they seem to be really important. And so when I started this, I went back to when I first started to really engage with some of Mickey's work, and it took me actually to my quals. And as a third-year student, I was thinking about one of my questions, I was dedicating a large part of it to Mickey's thought, and I described some of her approach as a structuralist theory, where, you know, she takes issues with the hypothesized role of domain general logical structures that, you know, you see in Piaget, and her argument is that content knowledge is not some paltry adjunct to cognition, merely to be analyzed by domain general logical structures, but is largely constitutive of cognition. And there was something in what she did that got to the kind of constructivism that I saw in education, but it was a constructivism that I could get down with. It was something where there's a way to operationalize what's going on. And so I thought one approach was to look for these big ideas. So what's the big idea? If we want to know about the structure of the domain, and are there certain big ideas that help provide access to this overall structure? How can we get learners to gain a purchase with these big ideas by engaging and then build upon them to build more knowledge structures? And so my domain of choice is mathematics. Why school mathematics? It's important for a lot of different reasons. So we talk about STEM learning, and something like algebra is important for obvious reasons as far as accessing STEM. Single biggest curricular indicator of whether or not you'll graduate college in 6 years is whether or not you took Algebra 2, right? But it's also tied up with some of the social concerns that I have as far as equity, you know, how early you get placed into algebra class and the kinds of outcomes it has on people's life chances. So I picked it because it was important, because it was complicated. There are lots of these arbitrary symbols people use. And then a lot of folks just don't like it or understand it. But the reasons why people didn't understand it was something that always got to me. And, you know, from my sort of unscientific observation as a graduate student over my desk, I had this thing called DSS theory. And what's that mean? Well, when people got math, they were usually doing some stuff. And I was a graduate student, so the second S was an expletive. But, you know, maybe what we need is some sort of knowledge structure to provide access so that they can engage and get more knowledge. So one of these big ideas that people have been talking about for 100 years, right, was the idea of mathematical equivalence or mathematical equality. And they've been talking about it theoretically as a big idea, and there have been decades of research on it as far as how good kids were understanding it or not. So here's this simple thing. 8 plus 4 equals 5 plus blank. But what do most kids, 2nd through 6th grade, put in? Like a 17 or a 12. Why? Because they're either adding it all up or adding to equal, because they aren't considering the equal sign as something that encodes a proposition, something relational, where this thing on one side and the thing on the other side, where there's a balance, where they're substitutable. So it's always been theorized as a big idea because it facilitates understanding of mathematics as a coherent whole rather than as a set of unrelated concepts and procedures. It's also thought of as a key strand in early algebraic reasoning. For my money, one of the most important things is because lots of these kids who are just doing some stuff do not see math as something that's supposed to be meaningful. And it's one of those earliest chances where they get to engage with mathematics as something that is about sense making. So even though it seems simple enough, here's this big idea that still 70% of these 3rd through 5th grade students, they just weren't getting it. One of the Martha Alabelli and McNeil studies, so first in 2009, but you find it all the way up. Lots of these kids are just getting this wrong. So here's something that, if it's a big idea, can we get kids access to it so they can access more of mathematics? And so my path towards translation was about chasing this big idea. And I'll talk to you about 4 different kinds of studies I've done on this, right? So the first kind is, just exploring what happens if we teach on this big idea as opposed to focusing on procedures. And I was also linking this with the sorts of self-explanations, because like with Kirsten, the self-explanation work, it really appealed to me from the beginning. In the 1994 paper, one of the points that she makes is, hey, look, the difference between what these kids, college students, are doing at the end of the day was not about individual differences in ability. They looked the same at pretest. It was about whether or not they were prompted to self-explain or not. So a lot of math work does want to look at individual differences, whether that be in working memory, whether that be in something like approximate number sense, whether that be in what have you. But a lot of those things aren't necessarily the most malleable. To the extent that some of these big ideas are something that we can get the focus on, then we have a lot of purchase and leverage. So the research questions here were, hey, does instruction on an efficient procedure or on the big idea lead to better learning in conjunction with the self-explanation? Does this type of instruction produce differences in the quality of self-explanation? And then does that quality is it predictive of learning? So really quickly, I'll just talk about one study we did with 2nd through 5th graders. What they got was either instruction that was focused on the concept or an efficient add-subtract procedure. Then they would do 6 math problems on a computer with accuracy feedback where they're asked to self-explain. They got a quick post-test and a 2-week retention test. As far as the kinds of measures, there were these conceptual knowledge of equal sign, sometimes like, hey, what's this equal sign mean? Sometimes trying to see if kids would accept different structures. Because lots of kids, when they see 3 plus 2 equals 6 minus 1, they will tell you that that doesn't make any sense. The equal sign has to come at the end. So these conceptual items, and then there are these more procedural knowledge items. And as far as what we got, if you look at procedural learning outcomes, the conceptual and procedural instruction, look at the light gray at post-tests, were about the same. And and you would expect that the procedural would be pretty good because here you got this instructed on this efficient procedure, whereas with the concept, we just talked about what the equal sign meant, but the kids were able to generate lots of different procedures, and then they also maintained it for a longer period of time. The big difference is when we look at these conceptual learning outcomes, that the kids who got conceptual learning, they learned a lot more. So here is a situation where instruction on this big idea gave us a 2-for-1. It improved this procedural and conceptual knowledge. And we also saw that it affected the quality of explanations. So the kids who, this is for each of the 6 questions they worked on in the interventions when they were asked to self-explain, the students who got the instruction on the big idea explained things in ways that were more conceptual in nature. And further, the frequency of conceptual explanations, it predicted both procedural knowledge gains and conceptual knowledge gains. So what we learned from this is, hey, look, this instruction on the big idea in this case led to these improvements in conceptual and procedural knowledge of it, so it's malleable, right? It led to these higher quality self-explanations, which was predictive of gains overall. So here we have this idea of this big idea that is malleable, that we can change around, but at this point I was starting to look at measurement issues in the field. right? So I wanted to look at some more construct validity. So, despite the critical importance of this equal sign stuff and understanding of equality, there's no standard measure of mathematical equivalence. And over the years, researchers have used these PET measures. Now, there are three basic types of measures people use, and they throw other ones in, but prior to some of our 2011 work, there wasn't even studies that were reporting on the validity or reliability of any given measure of equivalence knowledge. And there's lots of reasons that you want to have a way to compare against these. We want to be able to compare these research when people use these different measures. So with the next set of studies, what we did is we wanted to contribute to these abilities to study equality systematically, specifically by developing a valid and reliable measure of students' understanding of equality, creating a construct map. And construct validity is really key when we're talking about school learning. It's interesting, when I'm teaching classes and I ask my psych students, hey, what is math? What is a number? Sometimes they get a little upset. They say, hey, look, that's philosophy. I'm like, no, that's construct validity. That's part of your job. So, and we laugh, but a lot of what we're interested in is something. There are lots of times where people who are studying a particular domain are more interested in a general learning mechanism, something about change resistance or change blindness, as opposed to the math itself, which is fine. But if we don't know what we're looking for as far as what knowledge structures we want the children to build, we have a problem. So finally, I wanted to link equivalence knowledge to performance on some elementary algebraic items empirically. And like I said, there are a multitude of measures that people use. Most of them are either sort of solving these open equations, looking at whether or not kids accept these different or non-standard equation structures, and then sometimes they're direct explanations of what equal sign items mean. And so what you find is from study to study, people would use one set of objects as opposed to using them together, and we couldn't compare across them. So our first step was to make a construct map, and it's not worth having you read this. It's just a point to say that taking these different types of items in their different structures, looking at where they fit as far as a low understanding of equivalence. Hey, it means compute everything, to being able to explain the equal sign a little bit, to being able to use some of the properties of equality without doing calculations. And we were able to put different items where we thought they went on this hypothetical construct map. And after this, what we did was we used a Roche model. Why Roche model? It was easy, if it works. But we used a Roche model to help us evaluate our construct map. So we had this one parameter item response family, items from the item response theory family. And what it would do is give you a measure of both an item difficulty and of student ability levels. And so what this allows us to do, if it works, is A, in the process, we're going to determine whether or not these different items really seem like they measure a unidimensional construct. B is going to let us be able to see whether or not a student at a given ability level, what the probability is that this kid is going to be successful on a given item for a particular difficulty level. And we've looked at this with 4 different samples. I'll show you a map from the one we made with the 174 second through 6th grade students from a parochial school in Tennessee. We did it again with 220 kids from a suburban public school in Tennessee. We did it again with 229 7th through 12th graders at a small public school in Utah. And even though there are some things that change a little bit, we also used it with 182 developmental math students at an open enrollment university in Utah. And what we found consistently is that this construct map looks like it works. So we're confirming that this equivalence knowledge is this unidimensional construct that we can measure with these different items, but it's giving us a way to put these items on an interval scale, so it allows us to compare across different studies and also to make a higher resolution sort of study of where kids are or people are with their understanding of this construct. If we ask, hey, what's your definition of equal sign? It's one item, so you either get it right or you get it wrong. There's a lot of variability on either the right or wrong, and what this measures allowed us to do is to unpack that a little bit. So armed with the measures and armed with a little bit about malleability, we wanted to go back to look at this big idea and actually look at it versus some other factors, right? So some of the work that I've recently done with Lynn Fuchs starts with saying, hey, we've got all this theory that says that equal sign knowledge determines or affects or predicts algebra, but a lot of those studies are measuring them at the same time point. So can this equal sign knowledge in second grade predict how kids are doing with a couple of different algebraic, pre-algebraic items in fourth grade? And so for this, we use this data set. It was a Vanderbilt second grade math database. A bunch of kids measured at second and fourth grade. The key outcome measures were these two different algebra knowledge subtests. One was open equations with literal letter variables, which is sort of close to some of the open equations that we use with the blank. But then the other was understanding functions tables. And our predictors were a series of these sorts of equal sign knowledge items, but we also had other predictors. Eligibility for free and reduced lunch, WASI IQ, arithmetic, attentive behavior. And quickly to show you what we found was, I'm not going to go into the regression coefficients. These are just using standardized regressions as you're looking at it. But we found that fall IQ, fall attentive behavior, and spring math equivalence knowledge were the biggest predictors of how kids performed on these algebraic items in fourth grade. And if you looked at math equivalence, this big idea, it was the largest predictor by far. If you look at the unique variance by the Simmer partials, it was more unique variance than all of the other predictors we had combined. And notably, these typical risk factors that we look at, like free and reduced lunch, low early screening scores, they just weren't predictive in the same way that this big idea was. And if this was the truth for problem solving, it was also the truth for the function tables, which were a little bit more of a distal measure. So what do we find here? This equal sign knowledge in the spring of second grade was a strong predictor of algebraic sorts of competence in fourth grade. It's further empirical evidence for the link between this big idea and this further downstream sort of algebraic thinking. These effects are bigger than all the things that we like to think about, whether it's IQ, attentive control, eligibility for free and reduced lunch. The real risk factor was whether or not these students understood this big idea of equal sign knowledge. And so thinking about this conceptual difficulty as a risk factor is a big deal. Some of the next steps that we have going here are looking at more dynamic sorts of assessments. So how well does a student pick up this if we give them a little bit of scaffolding and a little bit more scaffolding and a little bit more scaffolding? This is the kind of thing that you can apply perhaps to a response to intervention framework where you're thinking about both the student's potential to learn versus what effect a sort of crystallized knowledge they have at the beginning is. But in the little bit of time I have left, I'm just going to quickly outline something that we're going to do going towards practical translation. So let's start with what we know. We know that these 15-minute lab interventions can lead to large differences in children's understanding of the big idea of mathematical equivalence. Now, there are some people working on a bigger intervention. Jody's one of them, but that's not out yet. So this big idea is key for developing mathematical competence. Importantly, this misconceptions of this big idea remain very prevalent. It's the kind of thing that appears for first grade Common Core, is going by second grade Common Core, even though work by Nicole McNeil has shown that second grade is when you start to see a decrement in kids, temporary decrement in kids' understanding of the equal sign. So the available practical educational resources fail to provide adequate attention to this, even though in lab studies we've seen that these quick 15-minute things can have a big effect. So the goal of this work that I'm starting up now is to adapt lab-based equivalence interventions for classroom use. We're going to space the practice with this big idea instead of just doing a single one-shot 15-minute thing. Do it 15 minutes a week, every week for 12 weeks. They'll be in small groups, prompted to explain and to talk to each other. And just a quick sort of skeleton of what this will look like will be a bit like this. So we start with third grade and sixth grade students. You have a group that starts off as a treatment group in the first and stage one, and another group that starts off as a control, and then they switch, right? So this one's treatment and control in 1 year, and then that treatment group over the next year will be able to see how long those effects are maintained, but the students that were in the control group will be a new treatment group, and we'll be able to, those kids will be in 4th and 7th grade now, but we'll also have year from 4th and 7th grade kids the year before, and this will all be done in a school so that we can look to see how this lab intervention that is translated to a classroom on this big idea, something that we've known works for a while, so that we can get something that's practical for teachers. So for quick parting thoughts, if I put the actual quote from the Chi and Ceci 1993 article that I talked about a little bit on, this was a chapter, and they said, look, today ample evidence points to the importance of content knowledge, not as an adjunct to cognition, but as a constituent of it. And this is to say that despite all the different types of learning there are, top-down, constructive engagement remains an important avenue, especially for school-based learning. Big ideas in certain domains can provide access for sort of getting that active cognitive engagement. And so to effectively promote this, we're going to want to continue to identify those big ideas to make sure we have sufficient measurement, of the knowledge structures that need to be involved, and then applying these sorts of accessible principles for encouraging constructive engagement. And this is Mickey's gift to me. And hopefully it can inspire some others as well. So thank you, Mickey and the little people. I bolded the people who give us the cash, IES, NSF, and Lynn's study was NIH, and NIH is also paying my student loans. NIH, I'm sorry. I love you. Thank you.
Okay, so our final talk of the session is by Jody Davenport. She's the director of the National Center for Cognition and Learning at WestEd, and her title is Studying Cognition and Learning in STEM Education, Opportunities and Challenges.
Yeah, so thanks for having me here, and thank you, Mickey, for inviting me. So I'm at WestEd, which I'm not sure many people in this audience have heard of, but it's an educational nonprofit based in the San Francisco Bay Area. So how did I get there? I probably am the most translated of all the people that have spoke. I started off as an undergraduate at UCLA working with John Hummel doing cognitive science with object recognition and analogical reasoning. I had a brief stint in Ireland working with Mark Keane in UCD, University College Dublin, on similarity judgments. From that, I went to MIT, where I studied attention, memory, and scene perception with Molly Potter. And then I had the opportunity as a postdoc to be part of the Pittsburgh Science of Learning Center, which Kirsten mentioned, which was really an amazing opportunity funded by NSF. We're bringing together researchers of multiple disciplines. And this is where I had the opportunity to learn more about Mickey's work, and really was influential in helping me become a truly translational researcher that applies work and cognition to meaningful application in the STEM disciplines. So what I did last in grad school was I was really interested in this idea about how our prior knowledge affects our perception. And the way I was studying it at the time was how does it affect your ability to extract meaning from a scene that you see for 80 milliseconds? And it turns out it does affect your perception. So if you know that you see something with the background that goes with it, your knowledge about what objects are likely to appear affect how well you're able to perceive a foreground object. And similarly, your knowledge about what kinds of objects are usually in the foreground affects your ability to perceive backgrounds. But my interest after the end of grad school, I was getting a little dissatisfied. I wanted to go bigger and really think about how do these findings really generalize beyond the lab, beyond 80 milliseconds. I mean, we live our whole lives, and usually we have the luxury of a little bit more time than that. So going into how do we get the knowledge that affects how we're perceiving things, and also really interested in how do we have learning opportunities that help people develop these kind of expert knowledge representations. I was particularly inspired by Mickey's work because she has this translational research on a number of ways. So first, her work began about really understanding the differences in how experts and novices structure knowledge, how they organize it, and what they do with it. She did a lot of work on conceptual change. So once you know that you want to get to the expert level, what are the stages people go through? What are the misconceptions that come along the way? And then finally, her most recent work has really been influential in instructional theory. So what kinds of engagement and learning help you get through the conceptual change and help people develop that knowledge? I'm going to talk about 3 different challenges of translational research and just give an example of some of the work that I've been doing. And then at the end, I'll say some of the advantages of doing this kind of translational work. So the first challenge, I think, is one of the challenges is how can we identify what is the relevant expert knowledge and how can we transform it into instruction? So I'm going to give an example from my work with Dave Yaron at Carnegie Mellon on equilibrium. So I'm not going to go into all the details of chemical equilibrium, but there was this problem that he was having with the students where, despite spending a lot of time trying to teach students how to solve equilibrium problems, they were just not understanding what was going on. And so when we partnered together as part of the Learn Lab, I was inspired by Mickey's nice paper that told you how to use verbal protocol analysis to try to uncover expertise. And we did a Think Aloud study using novices and experts solving this equilibrium problem that was really challenging. And what we found, perhaps unsurprisingly, was when novices were solving the problem, they were really talking about the numbers in the problem and manipulating the symbols to get the answer. Whereas when experts were talking through as they were solving the problems, they were constantly referencing the chemical reaction that was happening. They really were considering the chemical system, and they were using like hand motions to talk about this transformation that was happening as the particles were combining and coming apart. And so we decided to take what they were saying and try to make the instruction more explicit by developing new instruction. So the original instruction had been very quantitative based, and the steps and strategies were really about the procedures, not on the concepts. The new instruction that we developed was much more qualitative. So it was the exact same procedures, it was the way it was described that was different. And we made much more explicit connections to visual representations of considering this equilibrium system as they were given the instruction on how to solve these kinds of problems. And then finally, each of the steps was explicitly linked to what the experts were saying about the actual reaction, not just, okay, then you move this to the right, or some shortcuts the experts were using. So what we found in this was pretty remarkable. We found that if you look in the middle, more than half the people, double the number of students, were able to at least use the correct strategy or approach, just generally. Before they're getting so lost in the numbers, they weren't even really picking the appropriate way of solving the problem. And we also found that more than twice as many students were successful in completely solving these problems correctly. So in other words, by having this more, as Percival was mentioning, really conceptual ways of explaining, so by showing them the big idea, it really did help support their understanding and being able to solve these problems better because they had, so I think there's a win for the procedure and for the concepts. Next I'm giving you a little smorgasbord of the kinds of work I've been doing. Another challenge that we have when we're doing this kind of translational research is how do you apply multiple research-based principles in authentic settings? And I'm going to give an example from this, we call it the Math Center, the National Center on Cognition and Mathematics Instruction. That was a joint effort with WestEd, and we had 5 university partners. Julie Booth, who's here from Temple, was one of our PIs. We had University of Illinois Chicago, University of Wisconsin-Madison, Worcester Polytechnic Institute, and Carnegie Mellon. The motivation for this center was that there's a real disconnect between much of the cognitive research, what we know about how people learn, and many of the instructional materials that we have in place in our classrooms. So there's a lot of instructional design decisions that just don't take into account how people learn when they're being designed. I know some of the publishers are now hiring learning scientists and really making it more of an effort, but a lot of times the decisions about what goes into textbooks is about marketability more than learning. And we also had a challenge that much of the research that we have really is testing these principles in isolation. So they're testing one discrete process or one discrete thing. We have populations mostly of undergraduates, and the interventions are studied over a really short period of time in highly constrained settings. So our questions were, could we engineer more effective instructional materials if we apply multiple research principles to redesign an entire year of middle school math? And then the last part of the center was, so once we redesigned an entire year of middle school math using existing materials as a base, are these new materials actually more effective at promoting student learning? We had 4 principles that we had for designing the instruction that were based on cognitive research. One is the use of visual representations to really support connection building and learning, not just to be entertaining or fun. To give students practice, this is another reference to Mickey's work, really explaining worked examples of, so not just solving problems all the time, but really explaining why certain problem solving steps were correct or incorrect. To space learning over time and give different opportunities to practice. And then finally to use formative assessment, so how to help students both monitor their own understanding and help teachers monitor their understanding and adjust their instruction. To give you an example, so these are on the left is the original materials, and then on the right is the print materials. I don't expect you to see the details, but you could just see the first thing was, getting rid of a lot of the math materials are just, these fun pictures that are just for fun. And instead really replacing them with pictures that are helping the student solve the problem. This is an example of a worked example that then gives both a little bit more of a visual cue, and it also signals to the students that the part that was mostly correct, but the part on the right was incorrect, and asks them to explain what was going on with that. Just to give another example of how the worked examples and Julie's team led were interleaved was they give, instead of just this practice of solve, 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 explain is one of the tasks, and then also giving them the chance to see a partially solved problem and just completing it. So you're minimizing the task demand, so you're really having them be able to focus on conceptually what they're working on. We also had revisions to both the instruction and the classroom as well. So it's not just all in the print materials. To do the spacing and formative assessment, the teachers would give pre-quizzes to the students to really see if they had the prerequisite knowledge that they needed ahead of time. And then they would be able to give their students extra practice. There's kind of these maps of extra practice that they could give them if they needed to, if their students weren't quite understanding something that they would need to know to be able to build on that knowledge. I'm not going to go into all the findings. If you're interested, we finally had a paper that came out this year, and I can send it to you. But I'd say the lessons learned from this kind of translational research was that first, it's not easy to apply theories directly to practice, and I think all the researchers on our team all struggled in different ways and really generated some interesting new research questions by trying to make their research practical and applicable. So for instance, there were additional questions about how to use visual representations effectively, what kinds of explanations are useful, what is the right dose of worked examples, and also when you're talking about, we should space learning over time, well, what are you spacing and how? Are you spacing the content, the tasks, the response types? We also found that there were a lot smaller effects than in these large-scale studies because there's just so much more variability in the classroom over the long course of the year. And finally, there's really a need to consider the classroom context. There's a lot of different competing demands for teachers, and there's a lot of things that are going on with the student. If you imagine two undergraduates in a highly constrained lab study, they both have very similar backgrounds. There's very minimal variance between those two different scenarios, whereas you look at classrooms across the country and there's all different kinds of things that are going on. So that's things that you need to consider. So this brings me to the last one. This is related, I think, mostly to Mickey's newest work on ICAP. So we know that it's really important to get students to co-create knowledge with each other over time, and that's really the highest level of how to get students to really engage and construct their own meaning in learning. So the question is, what kinds of supports can we give to support this collaboration and construction of knowledge? And this is an example that this has taken me very far away from my cognitive science, hardcore basic research roots. But I just wanted to share it with you because I think it's important to consider what are all the things that you need to do in the classroom to set up environments where students can have these productive conversations. So this project is called Math Pathways and Pitfalls, and it existed at West Ed before I joined. And the fundamental idea is that they want students to learn by having explanations of correct and incorrect worked examples, by having classroom dialogues and discussions. So for example, the students would be given a starter problem, and they're asked to think about how they would solve this problem. But the real task is trying to get them to see that there's a correct way of solving it and giving an example of a student that solved it completely correctly, an incorrect way of solving it with a student who solved it incorrectly. And really the goal is to have these students have productive conversations where they're trying to understand and make sense of these problems by having productive conversations with each other. And this is related to Christy's work because she brought this up about how do you get the students to have these meaningful conversations? And you don't want to just say, I have an idea, and then the next person says, yeah, that's a dumb idea. How do you get it to be productive? So in this project, there's actually 4 days of professional learning that are offered before the teachers start using these materials that were developed. But I just wanted to bring up some of these points. So one of the things is that discussions, polite conversations and productive conversations doesn't happen spontaneously. It's really important for the teachers to create a classroom environment where this is safe, where kids even know what the rules are of productive conversation. This particular project has this poster that's kind of the framing of discussion builders. And what they suggest is that before you even start the materials of these comparisons, it's introduced about how do you have productive conversations. These are over 3 days, and so each you're just discussing about these discussion prompts, like these sentence fragments for how to have a productive discussion. So this is just an example about one of these, the one in the middle is expanding on others' ideas. So the teacher is given some suggestions to talk to their students about, okay, why it might be important to use these during the discussion? Like, how are these different from presenting alternative ideas? Why is it good to, say, I have a question about someone's ideas, or I would like to add to so-and-so's ideas. Then before they do the lesson, so we have a series, this was designed to help support algebra readiness skills in middle school. What we offer teachers a lot of different supports in the print materials as well. So one is these kind of a pacing guide. There's little indications about how the activity flows, which ones are in groups, which ones are in pairs, which ones are individual. Has prerequisite knowledge on the left, and it has some ideas for what the goals are. There's also information for the teachers about the research basis. We tried to provide information like, what does the research say? Why is this important for algebra readiness? Why are we focusing on these skills? And then we also have some discussion support and tips for English learners. There's also some more general, general prompts for teachers to use as they're walking around and engaging with their classes, and specific prompts for specific lessons. So these clipboard prompts are for all the lessons, and they could be for the teacher's whole class. Is how can you get students to not give them the answer, but get them to be thinking, so they are trying to think through things and understand the problem, understand the solution process, and talk to each other productively without giving them the answer or what to say. And then more specifically, there's also example for teachers how they might prompt students to think about this particular problem. What might they ask about it? So now I'm just going to transition so this is my sales pitch. So why should everybody do translational research? And also there's different levels of it. So I guess I'd say the lowest level, if you want to just dip your toe into translational research, I think it's really great to use STEM domains as the context for research on higher order cognition. We have these beautiful, deep, coherent knowledge structures that allow for problem solving and reasoning. So if you're just interested in that, use chemistry. It's great. It's a whole field. You have all these participants that vary on their degree of expertise that you could just use. And surprisingly, it's relatively untainted by everyday experience. So most people don't really know anything about chemistry, so you don't have to create your toy domain. You actually have this brilliant thing you can use. So using STEM domains in the sciences or math are a really wonderful way of studying some really important questions in higher order cognition, but being able to leverage that a little bit into the real world. The second level, if you're getting a little more crazy, you can actually investigate how students learn those STEM domains. So understanding the relationship between different cognitive processes or strategies, how do those things interact, if you wanted to study self-explaining or discourse or those kinds of things. And I think what's important is that really by making your theory more specific and tied to these domains and actually looking at student learning in real context, it forces the theories to be more clearly specified, and I think also then more generalizable, because it will apply to different things in the world, not just to the research or development materials. And it also has this added benefit of you can actually maybe help some people learn science along the way. And then the final layer is to really dive in and do research in authentic settings, which is messy. Recruiting is terrible. Schools are all over the place. But it really gives you a sense of all the factors that affect learning, not just the factors that affect learning in super constrained settings with highly motivated participants, but really how do you get students in general to absorb content and really develop more sophisticated knowledge. It's also, if you're interested as a learner yourself, you get to co-construct knowledge by really working on cool interdisciplinary teams with amazing other people, and it really does promote and make you a better learner. I've learned a ton by working with my colleagues who are also educators and instructional designers. And then finally, you can scale your findings for broader impact. And really, at the end of the day, the goal is, can we reach more kids? So can we get out there and have more students learn computer science skills or math or science? And I think that's the main motivation if we're really trying in authentic settings, is to get this really integrated research. And if that doesn't all appealing to you, there's also funding for it. So there's funding through both the Department of Education, through the Institute of Education Sciences, and also through the National Science Foundation. So thank you, and thank you, Mickey, for inspiring us all to be here. And with that, we have like 5 minutes. Does everyone want to just come up here, and then people can ask questions if you have any?